The next thing we're going to do is we're going to use radian measures to help us calculate linear speed and angular speed. They got a quick little definition here for each of these. The rate at which an object moves along a circular path is called its linear speed. So we're dealing with distances it travels along the outside edge of the circle, divided by the unit of time is called its linear speed. The rate at which the object rotates around a fixed point is called its angular speed. So now we're talking about how it rotates, how many rotations per unit of time. This one is how many feet, how many yards, how many inches, how many meters per unit of time. So the distance traveled versus the number of rotations it travels in a certain time speed. So linear speed is measured in things like miles per hour, while angular velocity is measured in revolutions per minute or second, or whatever time that you want to do. So the first one, linear speed, is always some type of linear measurement divided by a measurement of time. And the angular speed is how can you measure rotations around a circle, revolutions, rotations, divided by a unit of time. So they got a little key concept here. It says, suppose an object moves at a constant speed along a circular path of radius r. So we're talking about s, and s is rotating and traveling around the outside edge of the circle. Now that's a distance. We're going to measure distances in inches, yards, meters, kilometers, miles, and we're going to figure out how long it took to do that. If we do that, if s is the arc length traveled by an object during the time t, then its linear speed, velocity, a lot of times we'll use v for velocity, is s divided by t. Now that's just a distance divided by time. That's a linear speed. If they ask a different question, then they'll say if theta is the angle of rotation in radians through which an object moves during a time t. So now we're talking about the angle of rotation. It tells us how many rotations it's gone through. We give it an angular speed, and they use the Greek letter omega to represent angular speed. So since theta is going to represent some type of radian measure, which tells us how far around the circle we have gone in rotations or revolutions, we divide it by t, and we'll end up with our angular velocity, or angular speed. And we're going to use omega to help us with that designation. So in our practice problem number 5, it says, consider the DVD shown. Find the angular speed of a DVD in radians per second if the disk rotates at 3.5 revolutions per second. So the first thing we want to do is we want to consider what would theta be in this particular problem, because in order to work this formula, omega is our angular speed is equal to theta, which is how many rotations or revolutions or radians did it turn in a certain time unit. So here's the first thing we're going to conquer. It's going to take, and it rotates at a rate of 3.5 revolutions in 1 second. We don't want revolutions, we want it in radians. So to convert, what we're going to do is a unit converter. In 1 revolution, there are 2 pi radians. So every time we rotate around the circle once, 1 revolution is 2 pi radians, and we're going to get rid of our revolutions, and we're going to be back into just radians per second, which means we have 3.5 times 2 pi, and that's radians, over 1 second, which is going to be 7 pi radians per second. Okay, so that's the first thing we're going to do. And then we're going to place that in. So we got 4 omega. Theta is 7 pi radians per second. And we already have our time units involved. So therefore, we're pretty much through with this unless they want us to do some decimal requirement, which means you're going to take 7 times pi in your calculator and get somewhere around 22 radians per second if you want to go to that part of it. Next one, in 5b, if the DVD player overheats and the disk begins to rotate at a slower rate of 3 revolutions per second, find the disk's linear speed in meters per minute. So always trying to take a look at those units and make sure we know what we're going to finish our answer in, and we're going to finish in meters per minute. Okay, so this time it's 3 revolutions per second, and we're going to talk about its linear speed. Now, if it's linear speed, our velocity is going to be calculated by the arc length, which is how far it travels in a certain amount of time. So it's doing 3 revolutions in every second, so 3 revolutions per second, just like I started it last time. Only this time we're not going to go and put it into our radius. What we're going to do is we're going to figure out a linear distance that it travels. In 1 revolution, it's going to travel a distance of 2 pi radians. So then we'll have a distance of 6 pi radians per second. Okay. So that's part of the strategy here. Just a second, I got a little interruption. I'll come back. Okay, got that handled. Okay, coming back to this, what we have in this statement right here, it says we will have traveled 6 pi radians in 1 second. And a radian is the same thing as telling you you're going to travel 6 pi radii in 1 second. So if we got 120 millimeters, and that's the diameter, that means we've got 60 millimeters in 1 radius. And a radius is another way of saying radian. So to get a linear distance, how far do we travel in 3 revolutions around the outside edge of the circle? Well, if we did 6 pi times 60 of those lengths of the radius, we would end up with, doing a quick calculation here, 360 pi all over 1 second. So we now have 360 pi as a distance in millimeters, since that's what our radius was measured in 1 second. Now, we're going to have to get our final answer in meters per minute. So we want to get rid of millimeters. So the fastest way to get rid of millimeters is, if you think about millimeters, how many millimeters are in 1 meter? So in a meter, there's 1,000 millimeters. So now we are going to be in meters per second, since those are the labels that are left. But we don't want our answers in seconds, we want it in minutes. So we want to get rid of the seconds. So times, we're going to use a unit multiplier to get rid of those. Get rid of some of the confusion here. And we want the seconds to cancel out, so seconds and minutes. In 1 minute, there are 60 seconds. So our final answer is going to be a result of these calculations. What we have to calculate is multiply straight across. We have 360 pi times another 60. Our labels are going to be, the seconds will cancel, and will be in meters. It's the only thing left on the top. On the bottom, we got to take 1,000. And that's the only thing we have to multiply down there besides 1, so we won't worry about that. And the only thing we have left is minutes for our labels. So that's how many meters per minute we will travel. So to get a little bit better foothold of how many meters that is per minute, we'll multiply that. Calculation is 360, take it times pi, we take it times another 60, and then we can divide that by 1,000. In 1 minute, it's going to travel 67.9 meters per minute. Okay, so it's going to involve some unit conversions. Make sure you think clearly about the linear distance and linear speeds that it's traveling versus the angular speeds in which it is traveling.